Thank you all for staying. I'll be talking about quantum phase transitions in small, doubly connected superconducting cylinders. And quantum phase transitions are an active and interesting topic in solid-state physics, but being here at a nano conference, perhaps it's better to talk about the side effects that we are observing here. Many physical systems offer some kind of a typical length scale, like the correlation length or the other lengths that Roy has talked about, like wavelengths, like mean free path, and so on and so forth, and like a coherence length in a superconductor. And it's always interesting to ask what will happen to the system when the system will become smaller or comparable to this typical length scale. And this is exactly what we've done in this study. We've prepared a superconducting cylinder that the diameter is smaller than the superconducting coherence length. And in this case, it gives us the opportunity to see something new. The question, what will happen when the system becomes smaller and smaller than this typical length scale, is interesting if we see something new when this happens. And indeed, we see here something new, and the new thing here is this quantum phase transition that we'll be talking about. So I'll take David's suggestion, and I'll spend a few minutes to explain the title. And only then I'll give an introduction, and the experimental part I'll show how we prepare the samples, and then I'll show the results and try to sum everything up. So I come from a transport lab, and the main thing that we do, the main thing we did in this study is measure the resistance as a function of the temperature. Let's say I'm having some kind of a sample over here, I'm measuring the resistance, and I'm cooling it down. What can happen? Two main things can happen. One, the resistance can go up, and then call it an insulator usually. Or it can go down, and usually with some kind of a plateau at low temperatures, and then we say it's a normal metal. But there are some materials that at low temperatures, at a very specific unique temperature called the critical temperature, undergo a phase transition into what we call the superconducting state, where they lose all their electrical resistance. So the resistance is zero. Of course, most of superconductivity is in zero resistance, but for the sake of our study and for the sake of this talk, this is enough. This phase transition is similar to other phase transitions that we all know about, like boiling water or melting ice at the thermal. And so we see that if we cool the sample down, it turns to be superconducting, and if we heat it up again, it loses superconductivity. It turns back to be normal metal or an insulator, whatever it was before. And there are other ways to destroy superconductivity, and the most basic way, perhaps, is by applying a magnetic field. So if I have a high enough magnetic field, I don't have superconductivity. If I have high temperature, I don't have superconductivity. I have superconductivity only here at this S over here, only underneath this line, only if both temperature and field are low enough. This is for 99.99% of the materials, for bulk materials, most of geometries. So if I'm standing over here at this point of the temperature, and this is the phase diagram, this is temperature, this is the field, I'm standing over here, and I'm starting to increase the temperature, I'll see something of this measurement. This is the resistance as a function of temperature. When I cross this line over here, the resistance will jump up. I have alternatively, if I want to destroy superconductivity, what I can do is increase the magnetic field. I'm going here, I'm increasing the magnetic field. The measurement looks the same, but this time the x-axis is the magnetic field. When I cross this line over here, I'm seeing a jump of the resistance. So again, every time that I'm crossing this line over here, I'll see a phase transition from the superconducting state to the non-superconducting state. So this is the phase diagram. So again, this is the phase transition line, or if you want, this is the critical temperature as a function of the field. I want you to remember this phase diagram because later on we will try to produce a phase diagram of our unique geometry, and it will, of course, look somewhat different than this. Now, there is a very important and interesting point in this phase diagram, and this is a t equals 0 point. As long as the temperature is finite, bigger than 0, the phase transition is referred to be a thermal phase transition. It's being driven by thermal fluctuations. If you want, you have some kind of a competition between the energy of the system and the entropy of the system. But when the temperature is 0, you don't have thermal fluctuations. The entropy doesn't play a part in the game, and the only thing you have is quantum fluctuations that drive the quantum phase transition. So when the temperature is 0, the phase transition is called the quantum phase transition. There's more to quantum phase transition than what I've just said. This is only the first building block of the phase diagram. But again, for the for our study, this is, or for our talk here, this is enough. And this is what we're trying to study here, the zero temperature phase transition between a superconducting material and a non-superconducting material. So we talked about, I said what a quantum phase transition is, what superconductivity is, and very shortly, and we all know what a cylinder is. We still not need to talk about what is ultra small and what is doubly connected. So saying something in physics or in science, something is big or something is small, doesn't make any sense unless you compare it to something else. And in the case of superconductivity, we have two lengths here that we can compare a sample to. One of them is the penetration depth, denoted by lambda, not so important for our study, and it basically gives us the penetration of the magnetic field into a superconductor. The other one is the coherence length. The coherence length basically tells me the spatial variation over which I can change the superconducting wave function. So if I'm having superconductivity over here and I'm not having superconductivity over here, I can't do it instantly. I need to have some kind of distance to do it over which, and this is the coherence length. When I'm saying that my sample is small, when I'm saying I'm having a small cylinder, I'm meaning basically that the diameter of the cylinder is proportional to the superconducting coherence length. When I'm saying I'm having an ultra-small cylinder, I mean that the radius or the diameter of the cylinder is smaller than this coherence length. And the physics is different when you're comparable, when you're smaller, and when you're bigger. So, and last but not least, what is doubly connected? The doubly connected sample is a sample that contains a hole. So most keys are doubly connected because they have a hole. A bagel is a doubly connected bread, in contrast to regular bread that you buy at the bakery. If you want to marry someone, well, you should probably buy her an expensive doubly connected gold sample. So what did we do here? We prepared a doubly connected cylinder, that is, the superconductivity is only at the circumference of the cylinder. We applied a parallel magnetic field, and this is important that the field is parallel, and the cylinder is smaller than the coherence length. We measured the resistance as a function of temperature and field. From that, we got the critical temperature as a function of the field, and we built the phase diagram, and we compared it to the theory. The cylinder is thin, that is, the thickness of the cylinder, the really part of the superconductivity is smaller than the radius. The radius is smaller than the coherence length, and all of them are smaller than the penetration depth. The last one meaning that the Meissner effect is completely negligible. So we'll go into the introduction, and I'll try to do it short and friendly. I'm starting here with the Bohr-Sommerfeld quantization rule. If you want, this is the starting point of quantum mechanics. And what we need to do in this quantization rule is to do a path integral along the cylinder. M here is a velocity, V is a velocity, M and E are the mass and charge, C is the speed of light, A is the vector potential, N is a quantum number, and H is Planck's constant. And when you're doing this integral, the path integral of the velocity of what? It's a good question. Basically, you can refer to it as the velocity of the Cooper pairs. The Cooper pairs, the building blocks of superconductivity. If you take this velocity, multiply it by the charge of the Cooper pairs, that is 2e, and multiply it by the density of the electrons of the Cooper pairs, you get the supercurrent, the current running along the sample. So we're doing a path integral along the circumference of the cylinder, and the velocity just gains a factor of the circumference, that is 2 pi r, and the path integral of the vector potential, according to Stokes' theorem, will give us the flux penetrating the cylinder. This is similar to Aharonov-Bohm derivation, if you want. And when you play with it a bit, eventually you can get this term for the velocity. H is a reduced Planck constant, M is the mass, R is the radius, phi is the flux, and phi naught is the flux quanta, and N is the quantum number, and the system will choose the quantum number that will minimize the velocity and minimize the kinetic energy. And this is the basic physics behind all of this phenomena. Look at this plot over here of the absolute value of the velocity as a function of the flux. I'm starting here at 0 flux, and I'm starting to increase the flux. When I'm increasing the flux, the velocity will go up. The absolute value of the velocity will go up, and with it, the kinetic energy. When the kinetic energy goes up, the critical temperature will go down, and this will happen until I'm at this point over here, at half flux quanta. If I'll continue on to increase the flux, the velocity and the kinetic energy will go down, and the critical temperature will go up again. And when I'm over here at flux quanta, it's exactly as if I'm over here from the energetical point of view. And these oscillations will go on and on and on. And you can understand that these oscillations of the velocity can be translated to oscillations of the kinetic energy. And a mirror image you will have for the oscillations of the critical temperature. And this effect was measured about 50 years ago by Little and Parks, and is referred to be as the Little-Parks effect. And over here we see a measurement of the resistance as a function of the field. And this was translated to a phase diagram. This is the temperature as a function of the flux. And you can see these oscillations of the critical temperature. Now, the maximum degradation of the critical temperature, this delta T, equals the square of the coherence length over the diameter. They had a relatively small coherence length and a relatively big cylinder. So what they measured was a relatively small effect. I'm not sure if you can see it, but the maximum degradation of the critical temperature is half of a millikelvin. So this is quite small. But it's obvious that since the diameter over here is the denominator, when you make it smaller and smaller, these oscillations will become bigger and bigger. So you can put this velocity that we calculated previously into Ginzburg-Landau theory and get this expression for the critical temperature as a function of the flux. And let's plot it, do some numerical plots. So this is the critical temperature as a function of the flux when the radius is 5 times the coherence length. And look at the length scale over here. It's only 1%, and yet it is 20 times bigger than the oscillations that Little Parks observed. And if you want to see what will happen when we shrink the system down, we need to zoom out a bit. So this is the same plot. You can hardly see the oscillations over here because they're only 1%. And we're starting to reduce the diameter. So this is 3 times the coherence length, 1 time the coherence length. And here we have something special. When the radius is half of the coherence length, the critical temperature is 0 exactly over here. It's half flux quanta. So if I'm standing at half flux quanta, I'm reducing the temperature. I will never reach a superconducting state. If I'll continue to reduce the size of my cylinder, I'll have a gap opening over here at T equals 0. So now these red areas are the superconducting areas, and all the white areas are not superconducting. I'm not saying what they are. And if I'm standing at 0 flux, I'm standing over here, and I'm starting to increase the flux, over here I'll have a flux-tuned quantum phase transition. And this is, in order to see this, I need to have a very small cylinder. What is a very small cylinder? I need that cylinder will be smaller than the coherence length. So this is, if you want, one of the fascinating things about nano. It offers me the opportunity to see something new because of the size effect. So the previous theories, Ginzburg-Landau theory, and the plots that you've seen before, that you can see them again over here, are nice, but they have 2 problems. One of them, I was assuming that the thickness of the superconducting wall was 0, and this is, of course, not correct. And they're not so accurate because the way the theory is built on. There is a more accurate mean field theory that the result for the critical temperature is presented over here. The critical temperature is over here at the LAN and over here. These psi's are the gamma function, and this alpha is known as a pair-breaking parameter. This is a bad guy killing your superconductivity. Basically, in this system, it means the kinetic energy of the Cooper pairs, and this is the expression for alpha. So I plotted over here the critical temperature as a function of the flux for a few different cylinders with different sizes. So this is the biggest one, smaller one, and smaller ones. And you can see that at the end of the day, when the cylinder becomes small enough, the thickness plays a part. What does the thickness do? First thing, you can see that over here you have perfect oscillations. This point, and this point are all the same. But when you add the thickness to the game, this point and this point are not the same. And when the cylinder becomes smaller and smaller, the effect of the thickness is more pronounced. So this point is very much reduced in contrast to this point. And the reason that I want you to remember this lines over here, the area where R is about 0.4 psi, that this is the ballpark of what I measured. And this is the phase diagram that at the end of the day I want to produce again. So that's it for theory. We're going to the experimental part. Now, some of the pictures that I will show you are not appropriate for young children. So if there are some in the area, hide them away. This is a picture of one of our samples. So we start the experimental part at the Weizmann Institute with the aid of Hadass Strickman. She uses an MBE chamber to grow nanowires. that are either gallium arsenide or indium arsenide. They are 3 to 7 microns long, and the diameter is either 40 to 50 or 70 to 90, depending on the growth. And this is a typical semi-micrograph of such a gallium arsenide whiskers. We used both gallium arsenide and indium arsenide. And then we want to cover them with a superconducting material. So we put them in the sputtering chamber, where we sputtered either aluminum or niobium. Both of them are superconductors, and we covered them. So this is a typical micrograph of such whisker covered with niobium. You can see that this is 100 nanometers, so the diameter here is about 200 nanometers. And these are some more pictures that you can see here. This is aluminum that was without gold. This is aluminum with gold. Some of the materials, sometimes we covered another protective layer of gold to prevent oxidation. And this is another picture of aluminum. This is the final whiskers that we eventually worked with. You can see the diameter is about 100 nanometers. And as I said, the diameter of what Hadass is going at the Weizmann Institute is about 50 nanometers. So we can do some basic calculations. If the inner radius is about 25 nanometers, the outer radius is about 50 nanometers, it means that when I want to calculate the effective radius, it should be about 35 to 40 nanometers, depending on the specific whisker. And later on, we will see that this is, again, the ballpark that we are seeing when we are observing the data. So we have now a forest of this whisker standing up, and we want to find a good one. We want to create context to it, so we go to Sasha Sukernik from the Nano Center to help us do so. And I've prepared this super high-tech animation to show you how we do it. So we take a silicon oxide wafer and we cover it with a PMMA. And then we take this forest of whiskers and we push them against the PMMA, and a large number of them are basically being broken or left on the PMMA parallel to the surface. And then we go hunting for the good whiskers. We're looking for a straight one that has a good cover, that is long enough and doesn't have close neighbors or anything that we think that can prevent the measurements later on. And when we find it, we examine it for a few minutes with the E-beam. When we do so, it hardens the PMMA underneath it and changes its property. Later on, we put it in acetone. This will lift off all the other remaining undesired whiskers and all the undesired PMMA. And the next stage is to continue with standard E-beam lithography. And this is the output of what we see. Hard to see here. The whisker is over here. These are the ohmic contacts over here. These lines, 4 lines over here, in order to measure the resistance. So this is, again, both what we see, and this is the measurement system. We're running current from here to here, measuring the voltage between these two layers, getting the resistance, applying a parallel magnetic field. We're controlling the temperature with a dilution refrigerator that can go down to 70 millikelvins, that's 0.07 kelvins. Applying a parallel magnetic field, we can apply up to 8 Teslas, but 2 Teslas was enough in this experiment. And again, we measure the resistance as a function of temperature and field. So, some results. This is a niobium hollow cylinder. It was measured by Roy. He was a graduate student in our lab a few years ago. So this is a measurement of resistance as a function of flux. And you can see these oscillations. Now, this was measured at 2.18 kelvins. This is the lambda point of the liquid helium, so the temperature is quite constant. And you can see that the period of oscillation is about 600 Gauss. And what you definitely see here is that we're not observing here a quantum phase transition. And the reason we're not observing it, well, the first thing, you can see the temperature is high. And the physical reason that we're not observing here a quantum phase transition is that niobium has a very short coherence length, a relatively short coherence length. So what is short? Short in comparison to the radius. The coherence length of niobium is about 38 nanometers. The radius is about 100 nanometers. I can get this 100 nanometers from 600 Gauss. If I know the oscillations, I know the radius or the diameter of the cylinder. And again, so Xi swallows an R. This is similar to what Litt and Parks observed about 50 years ago. Similar, but not so similar, because when you look at this graph over here that we got from this data, this is a degradation of the critical temperature as a function of the flux. And we're looking at the maximum degradation of the critical temperature, we see is 2.5%. So this is about 160 times these oscillations are 160 times bigger than the little pulse oscillations, so if you want, these are not so little oscillations. So, yeah. This was not good enough. We wanted to have a smaller cylinder, so we went to aluminum. Aluminum has the bigger coherence length, the bigger one that we can use, the biggest one that we can use. And this is a measurement of the resistance as a function of temperature. This wasn't measured in a 4-probe configuration, so it's not the resistance, it's only the extra resistance. And this is a function of the magnetoresistance. That's delta R is a function of the field. And now this measurement was done at 70 millikelvins, and this is something different from what we've seen before. First of all, let's see what we're seeing over here. This is basically the superconducting state. Zero flux, we're seeing a very low resistance, or zero resistance if we want to subtract some kind of a constant resistance. At phi naught, we're seeing some kind of a finite resistance that is not the zero resistance and not the normal state resistance, some kind of finite resistance between the two. When we're continuing to increase the flux, we're seeing that the resistance goes down to a very low value, very close to zero, and then we're seeing some more oscillations over here. From the value of the resistance, the normal state resistance, we can estimate the mean free path using a free electron model. And we get from the mean free path, you can calculate the zero temperature coherence length to be about 72 nanometers. From the period of the oscillations, this 3800 Gauss, we can calculate the radius to be 41.6 nanometers. And if I double this, I'm seeing again that the coherence length is about the same order of magnitude as the diameter. So this is what I said at the beginning, a small cylinder. And very similar results were observed about 10 years ago by a Penn State group. They published it in Science in a very nice paper. And this is very similar to what they saw, mainly superconductivity here and here, and a finite value of the resistance between zero and the normal state resistance over here. And this is not good enough for us as well, so we prepared another cylinder that is even smaller. Again, this is a resistance as a function of temperature. This is a transition to the superconducting state. And this is a magnetoresistance, this time with the resistance, not the residual resistance. And you can see here somewhat the thing behaves differently. So this is superconductivity at zero field. These are different temperatures from about 580 millikelvins to 70 millikelvins over here. We're measuring, when we're increasing the field or increasing the flux, we're getting here the normal state resistance. If we continue to increase the field, we're seeing some kind of re-entrant of the superconducting state. And when increasing the field again, superconductivity is destroyed. So this is completely different in the sense that over here we're seeing again the normal state resistance. To the best of our knowledge, this is the first time that the resistance at phi naught over 2 at half flux quanta equals the normal state resistance. Again, we can do this calculation that we've done before. From the period of the oscillations, we can calculate the radius to be 33 nanometers. For the value of the resistance, we can calculate the coherence length to be 110 nanometers. And indeed, we can see that this time the coherence length is much bigger than the diameter, much bigger than the radius. And this is the reason that the resistance at phi naught over 2 equals the normal state resistance. And last but not least, we want to build up the phase diagram. Again, this is a mean field theory for the critical temperature. This is a measurement that we have done. What we need to do is to define some kind of criteria to define the normal state resistance from the superconducting state, normal state from the superconductor. So we define a critical resistance and we plot it over here. This line separates, above this line your normal, below this line your superconductor, and the intersection of these intersections of the critical resistance with the plots that we've seen before gives us points for the phase diagram. So these circles over here are translated to these points over here at the phase diagram. These are the red points that we can see over here in the phase diagram. The phase diagram gives us, again, the temperature as a function of the flux, and the blue line is a fit to this theory. Now, what's the difference between this plot over here and this plot over here? It's just the definition of the critical value defining superconductivity. Over here, superconductivity is defined to be 90% of the normal state resistance, and over here it is defined to be 80% of the normal state resistance. And the only thing that we want to show here now is that it doesn't really matter how you define the superconductivity, we can still fit it to our data. So we have reasonably good fit to mean field theory, and this is a good place to finish. So we observe the normal method to superconductor quantum phase transition. This is the first time that we know that the coherence length is indeed much bigger than the radius of the cylinder or the diameter of the cylinder. This is the first time that we know of this is the same thing, that the resistance at a normal state at phi naught over 2 at half-flux quanta equals the normal state resistance. And we can see that the mean field theory fits our data quite well. There are still, of course, a lot of open questions here. What is the role of the fluctuations, superconducting fluctuations in the phase transition? What are the quantum fluctuations doing here? What does the inhomogeneity of the cylinder will do here? What is the temperature dependence of the conductance is, and so on and so forth. But if you have a lot of questions, I think it's a good place to finish your talk. I have a lot of people to thank, mainly Alex, my supervisor, and Misha and Alex sitting over there in the back, my lab members, Ayal and Shkol, Hadass, Andrei, Yuval, and Georg from the Weizmann Institute, and all the solid-state basement. Thank you very much for your attention.
Well, one of the immediate questions will be, why don't we see actual zero ohm resistance in the superconducting state? When you compare it to the theory tells you that it needs to go to...
It's a good question. I'll try to go back here.
This is too beautiful to take out. Yeah.
I mean, you're asking me why over here it doesn't go all the way down here.
Yeah, I mean, when you compare if you go one slide forward, when you compare and you define some arbitrary value for the resistance, right? I mean, the theory that is for TC, and this is obviously not this is just a critical resistance.
Yes, so again, if I'm understanding you correctly, the basic thing you're asking me, why is the resistance that isn't going back to zero at flux quanta? And first of all, I'll show you a mirror image of what you're asking me. It's like asking me over here, why the resistance doesn't go over here to the full value of the resistance. To the full value. And the first thing that I need to tell you that I'm not sure about it. And I've consulted wise people, and I wasn't able to get a good answer. But I can give you some wise guesses, wise things that we are talking about here. So the first thing that can happen over here, there are a few mechanisms that will just give you a finite resistance even at the superconducting state below the critical temperature. I'm sure that you remember a Kosterlitz-Thouless transition in 2D electron, in a two-dimensional superconductivity, and a similar process that can happen in a one-dimensional sample is a phase slip. If you have something, think of some kind of a Josephson junction that you have inside your sample. This will cost you in the energy. So at a certain point of time, it's usually at a soft place, at a weak place in superconductivity will be destroyed. The phase will jump by 2 pi and then it will recover again. So if you want to see some kind of a fluctuation of the superconducting state, and this will give rise to finite resistance. So this is one thing that can happen here. And another thing that can happen here, that your cylinder is not homogeneous. So it's not an ideal cylinder that all the cross sections are the same. So maybe over here, basically, if I'm going back, one more slide here, look at the expression over here for the critical temperature. You see that it's the function of two ratios. A ratio of the thickness to the radius and the coherence length to the radius. The coherence length is proportional to the mean free path. If my cylinder is not ideal, and it is not ideal, of course, there are different cross sections along it. So there might be different critical temperatures. So at the same time, at the same flux, at the same temperature, this part of the cylinder can be superconducting, and this part of the cylinder can be normal. And this will again give me a finite resistance.
But then that will be sample dependent, right?
Yeah.
Then the criteria for RC will be sample dependent.
Not necessarily.
The inhomogeneity will not be cannot be repeated.
Not necessarily. Not necessarily. So it won't be a magic number that we're seeing over here. This value is not a magic number. It can be over here. It can be over here. It depends on all the parameters of the cylinder. Every cylinder will be unique in this sense.
Carbon nanotubes to your templates, but they are much smaller, and therefore you'd be further below the coherence length.
I'm not sure I have a good answer here.
Suggestion.
Okay, thank you.
just give one small comment. This year I was teaching the course on mesoscopic physics in the new program of material and nano research in our university. And actually what I was teaching, there are a few students that are still in the audience, you see. And I was one of the most important results, which was not, I think, for clear reason, was not really emphasized, Paul, but can you go to the previous slide?
Previous one.
All right. The most important, maybe this one, the most important actually result, which was somehow overlooked here, that you see that we go to the final resistance at phi over 2 of half flux quanta. And that means that you have a normal resistance, basically at zero temperature, for the disordered material. And if you remember, I was teaching you that one-dimensional system cannot be have final conductance at zero temperature. It either should be insulating or zero resistance state, because if it's superconducting. And this is the most important result here, that basically we have here really one-dimensional disordered metal which has final resistance. And this is really something new. And there is a big debate now starting whether there are additional system which was found also, a two-dimensional system which also should be insulating. Insulating means that in principle they should show some kind of increase when the resistance, when the temperature is reducing, they should show some increase in the resistance, some kind of what we call Anderson localization. So all the two-dimensional and one-dimensional materials should eventually, if they have slight amount of disorder, should go to infinity. And this system shows that it's not. And this is really very interesting and new. That's my comment to the students who were participating in the course.
Yeah, thank you very much for this comment. I think it's important not only for the students, but for everyone, at least for me. Any more questions? If not, first let's thank the speaker again.